So let's start. Alright, who doesn't know it? The Perseids are in August, so you would like to watch, what are they called? The things you wish on, but you can't see them always. And Jan Sundermann is looking at this. He's an engineer and astronomer, and he works at in spectroscopy at the observatory in, I forgot. Alright, thanks a lot for the introduction. About spectroscopy, we heard something earlier. So you inspect the light of stars and find things like exoplanets. Those are, of course, very advanced subjects. Where from flying space telescopes in space you can see, but also from telescopes on Earth. And there are a lot of different factors here which make this possible, such as the Perseids. You can even identify exoplanets, and we have this association, amateur observatory Neanderthal Hochtal in somewhere between Düsseldorf and Wuppertal, and you can imagine that is an area that is very densely populated and not the ideal place for astronomy. So we formed a working group there, and here are the names of that working group, of the members. And everything I'm presenting now is a collaborative work of this working group, and it also happened in a time without stars, this idea, and our idea was that we would look into light pollution for a bit, because we need, for one, a clear sky, but also a clean sky to make good astronomical observations. And you surely noticed over the decades that the sky at night is no longer really dark, and what kind of influence that has on people and animals and the environment. I don't want to talk about that, but we tasked ourselves to use our devices, our instruments, to inspect this light pollution a bit more closely, because it disturbs the visual observations and it disturbs even more the astrophotography and spectroscopy itself. So, as I said, this is the observatory in Sternhöhe, a bit to the right of this marker in the middle of the map. It's a bit east of Düsseldorf, which is down there. The bright point spot, that is Neuss, and above is Duisburg. So along the Rhine, you can see it's a very densely populated area, which results in this brightness at night. We can see with our own eyes. And this map you can find on the internet under this lightpollutionmap.info address, and you can check there for your own position, current data in this map. It's refreshed every couple of years, the data that's behind this, and then you can look where around you it might be a bit more dark at night, or if you really want to see the Perseids on an already bright summer night sky, where you might be able to drive a bit to have success in observing it. But a map like this reflects the absolute brightness of the sky in a clear night, and there are specific measuring instruments in astronomy. We use the magnitude as brightness, and this map was created through measurements from different positions. What we've done now, we're not directly interested in the absolute brightness, but we wanted to know what kind of light is that, what kind of colors are there disturbing our recordings. And we took out our spectroscopes for this and measured the intensity across the whole color spectrum. And it looks a bit like this. You can see those gray bars up there. Those are several recordings into different directions, which were put next to each other, where we can see these white spectral lines. So as mentioned earlier, the Fraunhofer lines in the presentation by Knut. There they have dark absorption lines, but here in front of dark background we have these bright emission lines, they're called. And these images generated with an electronic camera are evaluated by magnitude, and then you can see these curves down there in the lower part of the picture. Although those were also shown next to each other as above, so those aren't the absolute brightnesses, but you can see in parallel one curve has peaks, another curve doesn't have those peaks, or they're weaker. But what this is, that's the question now. So for observing the sky, we use these telescopes. And this is a mirror telescope. And next to it, on the lower left, there's this white box. And then in the back, you can see the body of digital XLR, I think it's called. And this is the digital spectroscope that contains the optical elements with which we can split the light that we see through the telescope optics. And for this measurement, we didn't use a telescope like this, but we wanted, as we'll see later, to be mobile with this. So we connected this spectral apparatus to a zoom objective, and with this zoom lens we made these sky measurements. But in the spectroscope itself, the most important element is a so-called reflection grid, I think, and that's a mirror with 200 lines per millimeter, and then that looks like a CD. If you hold it into the light, the light is split into its spectral colors, and then this signal is captured and evaluated.
Sorry, dann noch mit drauf zu schauen. Ist überhaupt noch jemand da?
Bitte?
Ja, genau, richtig. Die würden beide Breakouts, also beim zweiten kann ich dabei sein nach der Manuela, aber beim Jan jetzt halt nicht.
Uns interessierte jetzt aber in dem Fall.
And we are interested in
Super, genau.
the
Ganz so lang gelassen, weil ich glaube, wir hatten tendenziell eher ein bisschen Probleme mit der
light contamination and technique. And for this, in last spring, we took cloudy nights and took our zoom lens with the spectral apparatus and pointed into the sky in different directions.
Okay, das hatte ich
And
das heißt, wir machen beide Talks hintereinander und dann Fragen.
And then we measured these emission peaks, and then there was this, and then at the bottom of the scale we can see these lines that go up vertically. This is an extra calibration lamp where we can see neon light from a neon lighting bulb, which we added because those lines we know exactly where they are, and with those lines we can get a scale and then know the actual wavelengths of the other lines. So in spectroscopy you always work by putting the blue corner on the left and then on the right the red end of the visible spectrum. So on the left we have the short wavelengths, here shown in angstrom, and then on the right in red, going over into infrared, we see the long wavelights of the light. And what can really disturb such a recording is not just on the cloudy sky what we recorded there, but there can actually be these disturbances in a clear observation night as well. And this is an example from Harald from our group, who did a large area but weak object. So that's the North America Nebula, which is a cloud of gas and dust which shines by itself, and then in the curve below it, the red one, you can see the light pollution at the same location in a cloudy sky. And in the upper sky, in the upper curve, we can see several peaks or emission lines that are not in the lower one. And those are the emission lines that come from this gas nebula. And with suitable programs, you can subtract these curves from each other mathematically, and then you get the pure lines of the emission nebula of this gas, usually hydrogen and oxygen, nitrogen, and then you get those. All right. The light pollution that we have seen with these recording in the different directions, we wanted to identify this. Where does this come from? And so we took out our spectral apparatus with camera and the zoom lens, and we walked through or drove through the city and recorded some examples of different lamps. So from the street lights that we saw there. And this first one is the classic yellow light that you can see in street lights and also in industrial areas, often in industrial halls. So that's the sodium vapor lamp, I think. And that spectrum on the right, you can see the individual emission lines, because in this lamp, sodium is vaporized and then it shines in its fairly pure yellow spectrum. And here's a different example we found. The modern street lights with LEDs, where there are pure white LED lamps, as well as ones that are a bit tinted, especially where there's crosswalks, I think. And you can see a big difference to the image earlier. This LED lamp, because it's supposed to shine white, it is composed out of a big area in the visible spectrum. Also has a peak in the red area, but at the end you have there all the different colors, and it's a big, it's almost a normal distribution of these wavelengths, so that you can already imagine this is difficult to filter out. And in between we have the generation of street lamps with these fluorescent lights, which might contain quicksilver, which is a metal that's vaporized in this lamp and then has a single sharp emission line. And we have very different kinds of emission from these very different kinds of methods of illumination. And these individual spectra from the different light sources we took and made an image of this whole contaminated, of this cloudy sky and associated them, and you can definitely see, find them in there. So you can see the peak of the fluorescent lights, or also the natrium, sodium area with the closely clustered lines, and you can see all this in the light that gets reflected from the cloudy sky, and which we then also get in a seemingly clear dark night, and it's still in there. Nonetheless, there are still lines here which we have not observed, so there are still other light sources that could be, for instance, vehicles, so xenon or those halogen lamps, or in Düsseldorf itself there are streets, and in the old city there are parks and sidewalks which are really lit with gas lamps. So gas is actually being burned there, and those lamps are protected monuments, and those might also be in here, but we have not identified this closer. We wanted to see what is going on there and what kind of lights are disturbing their observing the sky visually or with photographs. And the conclusion is that it has gotten worse due to this LED light, because this sodium light can be filtered out. You can take a filter that's designed for this, which just filters out a small area of the spectrum, and then you have the information of the rest of the spectrum to the right and left of it. You have that in your image, but the disturbing light of a single sodium lamp or a single quicksilver one can be filtered out through a good filter when taking a photo. But with this LED lamp, that's more difficult, because we have seen it's almost a normal distribution across the whole spectrum, the emission lines, and you can't really filter that out. You would filter out all the other information as well, so, and destroy this information, so you wouldn't have anything left in the measurement. So one important realization is, and we communicated this to the people from the Urban Works, I think, as well. If you take this LED lights, which saves energy, then you should also go so far that you make it very targeted lighting technology in the city, and avoid as much as possible having light leak into the sky, and also maybe control the lights so that if nothing is there, no traffic, then maybe you can turn them off as well. There are also smart systems for this, of course. So this is our conclusion. We can do a lot with filters. With LED lamps, we can't do anything. We can only call upon the responsible places to do responsible lighting of only where you really need it, and ensure that there's as little leaked light as possible. And this whole subject that I described now, we have created 2 posters about it as well, one in German, one in English, was presented at the last Congress in Lübeck. And they're at VDS Astro, so that's the Spektroskopie conference. You can download them as well and distribute them wherever you want, if anyone's interested. And the poster is available for free use. Yeah, thanks a lot for paying attention. Slightly complicated subject, but very concrete one. So in astronomy, we're not only looking at very exotic things. We can also use our devices for very